Happy New Year, Living Environment friends and fans and families and followers, and don't forget to like and subscribe in 2022, baby. Yep, we're back for another year of Living Environment, and we're going to start this year small, very small. Let's do that. All right. Hey now. Mr. Kovacs class. It's Mr. Kovacs class. You might learn a ton. It's Mr. Kovacs class.
He's interesting too.
It's Mr. Kovacs class.
And he's super cool.
It's Mr. Kovacs class. We're going into the realm of the small, the tiny, le petit, klein, and yes, the small, right? Here, so I found, this is a website, and I'm going to take you through. We actually already studied when we did, remember we did diffusion, and we had those gelatin cubes? Remember that? Yeah, and that was to prove why cells have to be small. Now I guess we're just trying to figure out, well, okay, exactly how small are they? So we're going to zoom in to some small things here. There's a grain of rice. There's a sesame seed. There's a grain of salt. Now we're reaching the biggest cells. So the biggest cells are about a little bit, half the size of a grain of salt. And the biggest cells are these large unicellular organisms like amoeba proteus, the giant amoebas. You're probably familiar with them. In fact, paramecia are big cells too, because they're, one cell critters. It's actually kind of an advantage to be since you only have one cell to do all the work, you want to be as big as you can get. But there's a limit to how big you can get because you have to diffuse through the membrane. You can see here the largest human cell are human egg cells. And we'll talk about those obviously later when we talk about reproduction, but egg cells are reproductive cells. Let's zoom in a little bit closer here. What do we got here? All right, some typical cells. Skin cells are kind of an average size cell. They're fairly big. We measure cells in what's called micrometers, or 1/1,000,000th of a meter. So this is 31/1,000,000ths of 1 meter. This is a rod cell that you'd find in your retina of your eye. A pretty big cell, but kind of long and skinny. And we'll talk a little bit about like that. Often cells in multicellular animals like ourselves or plants or beings, their cells are designed, the shape of their cells are because they have a particular job. They don't have to do everything. Right? Whereas like the amoeba is kind of just where are you, amoeba? You're just a big blob because that one cell has to do all of the life processes. We have obviously multiple cells to do that. Of course, little red, hey everybody, they're quite small cells, right? Little red blood cells are very small. And you know what their job is just to basically carry oxygen in hemoglobin, right? Really small. Right, so if this was 30 and this is 8, they're like 3 times smaller than a skin cell. There's some of the smallest cells that you have, actually. And then we get into, let's see, yeast is pretty small. Yeast is a fungus. We'll talk more about them, but yeast, of course, are famous for doing fermentation. That is, they can make alcohol when they break down sugars in the absence of oxygen. All right, chromosomes, we'll talk about them. Those are actually cell parts. In fact, here as we get small, the parts of cells, like mitochondria and lysosomes, are pretty small. But then bacteria, I don't know if you got, bacteria are one-celled critters. They're some of the more ancient critters. They're really, really small. So one bacteria, like a strep or something, is about the same size as one mitochondria inside one of your skin cells. All right, so think about it. You could fit, right, they're about 1 micrometer long. Skin cells like 30 micrometers. So you could fit 30 bacteria across the skin cell in each direction, right? And then, so it's like, what 30 times 30, 900 bacteria can fit across inside of this cell. And that's assuming the cell's just flat. All right, and then we're gonna go even smaller. Now we're into the realm of not even cells. Viruses are even smaller. You know, this is why the original debate with masks, you know, one of the arguments against masks was like, look how small these virus particles are. How can a mask stop them? And what we learned at first is, people weren't sure, but we learned that what happens is these virus particles, especially corona, they travel in snot droplets, like droplets of mucus. And so they get caught in a mask, not because they are big enough to get caught, because they're usually clumped into big droplets of mucus. Hopefully that makes sense. That's why the masks work. Okay, they do work. What else we got here? Some really small viruses. Rhinovirus, that's like the common cold. And what else on this? All the way down. Now we're into just molecules. Right, an antibody, which we've studied too, is a big protein or glycolipid, and it's fairly big, but it's still much smaller than a cell. It's now measured in the billionth of cells, the nanometers. Nanometers are 1 billionth of cells. Okay, and then what do you think the smallest thing on our list here? I wonder if it gets down to like the size of an atom. Yep. Look at that, an atom. Picometers. Right? Water, really small. All right, so let's zip back out. So we're going to be going to the realm of the small, so I'll be talking a lot. We'll be working with microscopes. Boy, I've already talked a lot.